Okay, let us start. Welcome everybody for today's IBSA webinar. The webinar title for today is In-situ measurement and model calibration, especially for a case study based in Salford University future home project. We have three fantastic, very experienced presenters today, all from Salford University. They are actually sit down in the same office and will present today's topic for us. So the first speaker is Özlem Duran, lecturer in sustainable building technology. She worked for both industrial and academia side for quite a long time. And also she is my former colleague, which I just noticed in Nottingham Trent University, and she got her PhD from Loughborough University. So she working in Midland quite a long time, and Lincoln University as well. Also, she worked for industrial, such as the big company Arab, and also the consultancy company retrofitting coordinator for she founded the consultancy company Carbon Lift and work for that company, focus on the building performance analysis and the life cycle carbon analysis. Then our second speaker, Grant Henshaw, she is a key person for the energy house. She maintains the energy house as a daily working technician and researchers. She have experience in the measurement of the building fabric and the heating system performance in both laboratory and fieldwork siting. He has delivered numerous research projects for commercial clients and work with both government and industrial, which he will introduce in detail later on. And the third speaker, Dr. Chris Tsang, he also graduated from Loughborough University, but now working for Salford University as a fellow and lecturer. He also worked with Leeds Beck University for quite a long time, focused on the government-funded project based on the thermal bridge modeling. And that's our three speakers' background today, and they will introduce more detail later on. About our group, all of these theories webinar funded by IBSA, International Building Performance Simulation Association, and our group is particular focused on the education, deliver the knowledge for all of the audience. So we have three objectives. As you see on the screen, identify the education and the training needs through the building simulation performance community, and also to initiative, develop and encourage collaboration for the new education materials and methods, and offer the training sessions for both members and non-members. And for today, we will go to the presentation first. Listen our three fantastic presenters present their work. And then we leave about 10-15 minutes for question and answers. Then I will introduce a little bit our future event. So welcome you register for that event as well. Okay, so now floor open for our presenters.
Thank you very much, Ho. I will be sharing my screen.
Yeah, I will stop my share. Yeah, you can share now.
Right. Are you able to see it in full?
No. I cannot see the share screen yet.
You cannot?
No.
Okay. Are you seeing the PowerPoint?
No.
How
about the others? Can you see the share screen? Jianfeng, can you see the share screen now?
Not really.
Maybe you can send to us.
I'm trying again.
Yeah,
it's coming. Yeah,
it's
coming now.
No, okay, maybe it delayed for some reason.
Yeah.
Okay. Right. Great. Thank you very much, everybody. Welcome. Just a second. Yeah. Thank you for joining us today. I'd like to introduce you to the Energy House Labs briefly before handing over to Chris and Grant. The Energy House laboratories are one-of-a-kind world-leading research facilities at the University of Salford that are forging the way in making our buildings carbon neutral. We have 4 labs, Energy House 1, 2, Thermal Measurement Laboratory and Smart Meters Lab. Today we are going to be focusing on Energy House 1 and 2. Energy House 1 focuses on retrofit and the 2 is on new build. As you know, UK has the worst performing housing stock in the EU, and 80% of the homes to exist in 2050 are already here built. To meet our 2050 net zero targets, 27 million homes need retrofitting. That's 900,000 homes per year and 2,466 homes per day. Therefore, the research on retrofit emerged, hence Energy House 1. Energy House 1 is a unique research and testing laboratory and comprises an early 20th century 2-bedroom terraced house within an environmental chamber, allowing an accurate and rapid assessment of energy-efficient retrofit technologies. Quite a few type of research is ongoing. These include building performance, data sensors, data collection based on sensors, data analysis, visualization, human factors, and smart meters connected to homes. I hope you see the video. Energy House 1 was built in 2011. It's a traditional construction, solid brick walls, suspended timber floors, and single glazed windows with a conventional wet heating system fired by a gas boiler. The environmental chamber can be used to simulate a wide variety of weather conditions with a temperature range from -12 to 30. The chamber is also equipped with rings to simulate wind, rain, snow, and incident solar radiation. Energy House is a fixed asset reflecting 20% of the UK housing. Due to limited weather profile and waiting times for testing over a year, the urge for Energy House to came in. That's why it's built after a decade than the Energy House 1. Grant will introduce you the details of it in a minute. Before that, though, I would like to share you a very exciting news. We are in the process of organizing a retrofit conference to be held in the beginning of July 2025. And the call for abstract is going to be out very soon, actually, within this month. It's going to be related to anything and everything about retrofit, occupant design, scaling up policies, but performance and evaluation specifically is quite relevant to the audiences of this webinar. So I would like to welcome you to our conference and send your abstracts. Please do contact us. Energy House Labs, the website will be involving the conference's website as well. And also you can find us on the social media. And please do not hesitate to email us if you have any questions or anything related to conference or the labs. Thank you very much. And now I will hand over to Grant.
Okay, can you see the screen?
Yes.
Yeah, well, thank you, Özlem. So welcome to our presentation on in-situ measurement and model calibration. We'll be focusing on one of the properties at Energy House 2 throughout this session today. My presentation will focus on the experimental side of the research, and then Chris will follow on from me, explaining how we took that data and calibrated a model based around it. So first off, as Özlem said, we're a collection of labs, Energy House labs. Energy House 1 built about just over 10 years ago now. Thermal measurement laboratory, which UCAS accredited, smart meters and smart home lab, which looks more at mass data sets and data analytics. And then Energy House 2, which was built about 2 years ago now. So Energy House 2, quite a large facility, really. It's about 8 times the size of Energy House 1, with much greater weather conditions that we can set. So we can go from -20 up to +40 degrees, simulate rain, sun, solar radiation, and wind in these chambers. So using that array of capabilities, we can simulate about 95% of the populated world's weather conditions. Another thing that's key to note here in this video is that you can see real soil pits, which allows us to build assets, 2 fully detached houses per chamber, and then once we finish testing them, deconstruct them in a sustainable way and build new assets in the place, so we're no longer stuck with the one property. We have 3 HVAC systems per chamber, which power it all. So as far as we're aware, we're a very globally unique facility. And we're looking not just at UK-based architecture, but also worldwide. So today we'll be focusing on one of the properties within what we call Chamber 1. So this is the Bellway property called the Future Home, and this is time lapse of it being built. Probably about a year ago, just over a year ago now. So it was off-site construction. It was timber frame construction on site then. Build, you can see all the different heating systems being installed. There's an array of heating systems, more than would ever be put into a typical house. That's simply for us to be able to quickly change between them for our different test scenarios. To quickly go through them, there's 2 variations of infrared heating, underfloor heating, traditional radiators, and then also 2 different types of air source heat pump in the property as well. One is roof mounted and one is ground base mounted. So we can switch between them rapidly and test the performance and thermal comfort of the different heating systems. But today, we'll be focusing on fabric performance. We'll just wait for this video to end on the flyby, so you'll get a look inside the property. It should be noted the property is fully furnished as well, so it won't be in this video, but all that thermal mass that is typically there when it's occupied is also there for all our measurements. We can have people living in these properties overnight for short periods of time, which is something we couldn't do at Energy House 1. So it allows us not only to use EPD and PMV metrics when we're looking at thermal comfort, but also actually get real occupant sensation and feedback. So why these 2 houses? The Future Home standard is coming in next year. So that's a 75% reduction carbon compared to 2013. More efficient fabric and air tightness for buildings going forward. Lower running costs, and then other electrical systems and energy systems. So as I said, we have 2 properties. We have Sangaban and Barrett's E-Home 2, and we have the Bellway Home, which is the Future Home. So this is a brief overview of the different systems that are installed within the Future Home by Bellway. As I said, we'll be looking not only at the fabric, which the report is currently out, but also all the heating systems, overheating risk assessment, and also thermal comfort and energy systems. So how did we characterize the fabric performance? We looked at 3 main things. That was the whole house heat loss, which is the HCC. We measured that through the coheating test, which is the standard way of measuring it, but then also rapid solutions and rapid experiments, which is the cube method and VeryTherm. We also looked at U values on every element within the building, and then also air tightness testing through 2 different methods and alongside a thermographic survey to try and disaggregate where the air leakage is happening. So typically in a coheating test, when you're doing it in the field, you have to account for solar radiation. You have wide variations in temperature and different conditions, wind, rain, so on. So you're typically looking to run the coheating test for about 2 to 3 weeks. You create a steady state environment internally, but you have no control over the external world. When we do an energy house, because we can emit solar radiation and we have full control of the external environment, we can create a truly steady state setup. So we just look at daily average power consumption and divide that by the daily average delta T. We can do this typically in about 3 to 5 days. As I said, it's steady state and we emit solar radiation. Similarly, when we do U-value measurement, again, a much shorter period than you would need in the field. And because it's a steady state environment, we can look at 24 average heat flux through the fabric divided by the 24-hour average delta T. We did all the U-value measurements in accordance with ISO 9869, so they all lasted minimum 72 hours and all conditions were achieved. Air tightness, we used 2 different methods. We did the fan pressurization test or the blower door test. This creates an elevated pressure differential across the property, but a benefit of doing this method is you can do thermography at the same time and trying to work out and diagnose where the actual air leakage paths are. We also use a pulse test, which is a much faster test than the blower door method. And it's also a smaller pressure differential, so more in line with what you did experience in day-to-day life. So I've included this slide to show how stable the measurement is within Energy House 2. So here you can see the daily power consumption from the orange bars. You can see the daily DT and how little that varies. And then you can see the daily average HTC plotted with the black dots and then the average over the full 8-day period. So you can see it's a very stable environment that we're working with here, and it allows us to not only get faster measurement, but typically more accurate and less uncertainty our measurement because there's less fluctuation in our data. So the results, whole house heat loss, you can see the design HTC there, which was roughly about 79 watt per Kelvin. And we can see there was a performance gap when you look at the coheating test. So it achieved about 82.2 watt per Kelvin. So not a great or huge performance gap in any way. Cube test, similarly in line with that, slightly lower than the design, and very therm, slightly higher than the design. In air tightness, it actually had quite a big performance gap. However, as I said, there's multiple heating systems installed, and I'll go into that in more detail. And you can see the blower door result was 4 meters cubed per hour per meter squared. Pulse, when extrapolated to 50 Pascal pressure difference, was 3.25. And the design was 2.5. So there was a bit of a mismatch between what Bellway designed it to be and what it actually achieved. This is quite a large table for a PowerPoint, so I'll skim through it briefly. This is how, well, you can see the design U values for every building element. Each building element had an array of about 9 heat flux plates attached on it, and then wherever there was a repeating thermal bridge, we affixed another heat flux plate to that area so we could balance out the average U value for that element. You can see there was mismatches, typically underperforming on some elements, but also overperforming on others. And here, where you see heat loss, this is where we use for the plane element analysis. So you take the U value that you measured for that element, the total surface area of that element, times it out to get a watt per Kelvin figure. And this helps us disaggregate the measured HTC from the coheating test. So here you can see the HTC design on the left-hand side, and below that HTC measured from the coheating test. The total of them bars is what we measured from the coheating versus if you do plane element analysis on the design or from the SAP sheets. As we build it up, you can see there's quite a significant difference between infiltration heat loss in the 2 design. And measured values. However, fabric performed fairly in line with each other. And on the right, you can see what proportion of the fabric heat loss was attributed to each building element. So what does it all mean? So whole house heat loss was ultimately 7.7% worse than the design. However, as I mentioned first, it has much more heating systems installed in this property than you would ever get in the real world. So that meant far more penetrations through the building fabric. So that is where it came out of cost to the air tightness of the property. So air tightness was 61% worse than the design. And also, when we did the thermographic survey after doing the blower door test, we found that loft insulation was disturbed, and where it had originally been laid flat by the installers, when you get all your contractors in, such as electricians, plumbers, and so on, unintended consequence of installing all this stuff was it got disturbed and became quite patchy. So we found the ceiling in general underperformed by about 56%. However, we believe we can rectify that down the line, and we're looking at a piece of research to do this, to see is there ways of mitigating them issues of installing loft insulation. Windows and doors generally perform well, and also the floor did. However, there is a significant issue with how we measure floors. Trying to do a spot measurement with a single heat flux plate to try and represent a full floor just isn't ideal, because there's so much that can go into the complex design U value of a floor, such as geometry, perimeter losses, and so on. Trying to get an average heat flux plate measurement for all that, you're always going to get some level of discrepancy. So ultimately, air tightness could have been improved, but we believe for our next set of testing regimes, such as systems reporting, overheating, and so on, we're going to stick with the house as it is. So we have the pure baseline measurement, and then see how the systems perform against that baseline, instead of adapting the house and trying to improve its fabric performance. And as I said, there's overall 6 different heating systems in this house, which you just would not install in the real world, leading to many penetrations. And as I said, loft insulation, we're going to look at is the ways in the future we can install it in different ways to mitigate the risk of disturbing the loft insulation. So ultimately, the reports are out for the baseline fabric reports for both properties. They're both about 100 pages each, so it's a nice fun read. But it's important, I think, to measure it under control conditions, as it gives us a good jumping ground between modelling and then trying to calibrate models without all these variations that you get in the real world, which would lead us on to Chris's presentation in a moment. When we've measured the performance gap on new builds in the field as academics, we found gaps up to 140%. So when I say that the Bellway property had an 8% performance gap, if you compare this against the Leeds Beckett coheating database of new build homes, you can see it. Although we want to improve it, it's not a huge issue compared to other dwellings that they've measured. So that concludes my experimental side. I'll introduce Chris now for how he took this data and calibrated his design builder model.
And 2 presentation. Yeah. Need to minimize it. Okay, you can see it. Hey, so hi everyone, I'm Chris Tsang, and today I will talk about the in-situ measurement and model calibration, a case study on the future home. So Grant has already talked about the measurement side, and now I will talk about the methodology and the results of the model calibration. So just a recap, this is the Bellway, the future home. So this left top left figure shows the front view of the house, and the next one shows the back of the house. And you see we modeled the whole house in Design Builder with all the wall lengths, window lengths, all the areas, all the volumes built exactly to the house located in the Energy House 2. So this is the render view of the Design Builder model. And then this is the floor plans of the Bellway house. So it's a 3-bedroom detached house with a living room and a kitchen diner in the ground floor. And then there's three bedrooms in the first floor, and then a bathroom and also an ensuite. So I want to talk about the design parameters step by step so that we all understand what we entered the parameters to Design Builder. So first is the external wall U value. It's 0.18 by design, which is the same as the Future Home standard. It has 7 layers. It has 102.5 millimeter of brickwork, 63 millimeter of ventilated cavity, 9 millimeter of OSB board, 89 millimeter of mineral fiber insulation with timber frame, 40 mil of PIR insulation board, 25 mil or 38 mil of surface void with wooden battens, and 15 mil of gypsum plasterboard finished. And then it's the rendered external wall U value, which is the white bit you just see in the Bellway house in the front of the building. So it's a bit lower U value than the external wall U value by 0.01. The build is basically the same, except there's a 22 mil of render and 100 mil of block work at the front, replacing the brickwork, and the others are all the same. Then the loft ceiling is a bit lower than the Future Home standard. It has 500 mil of mineral wool insulation laid between joists in layers, and then applied onto 12.5 mil of plasterboard. The ground floor U value is 0.11, a bit lower than the Future Home standard. It's an EPS-based insulation precast concrete slab system. Air permeability rate is 2.5, a bit lower than the Future Home standard 4 or 5. Here you see 2 values because in Future Home standard there's 2 standards. Option 1 is 4. Option 1 is 5, which is a less stringent standard, and the other is the more better towards net zero standard, which is number 4 for air permeability rate. So for Windows U values and Windows solar heat gain coefficients, they are all sourced from manufacturer specifications. They align with the Future Home standard, same as the external door is a PVC with steel reinforced frame. The French door is the large patio door which located in a kitchen diner. It's a bit higher than the normal windows and is sourced from manufacturer specifications. The unoccupied pitch roof U values, intermediate floor U values, and internal partition U values are all sourced from the information from the house builders. So the construction are here shown below. And also these U values are all entered in Design Builder. So besides building fabric inputs, we also need thermal bridging inputs. So a bit of an overview for Y values is to divide the thermal bridging heat transfer coefficient by the total area of the dwelling's exposed element. So the latest version of SAP 10.2 maintains a default Y value of 0.2, where the Future Home standard maintained a Y value of 0.05. So in the Bellway reports, we calculate all the thermal bridges using Trisco, which is a thermal bridging modeling software for every junction. And we calculate a Y value of 0.05, which fulfills the Future Home standard. So here we show all the psi values, which is input to Design Builder. So as Grant talked about the in-situ measurements, they can be used in the models. So we put heat flux plates in 57 locations, which measures the U values. And you can see the external wall U value is a bit lower than the design value. And the rendered external U values is the same as the external U value measured. The loft ceiling is a bit higher than the design value, same as the ground floor value. Note that the ground floor is a point thermal transmittance, PTT value, because as shown in here, this figure, For example, there's 9 points measured using heat flux plates on the floor. You can see 0.3 is 0.24, but 0.4 is 0.11 for the U value or PDT value, which is 2 times difference. So it depends on where you measured the U value of the floor can give you very different results, and it's quite a difficult metric to measure. So but in this measurement, we get a 0.14 PDT value. So note that for windows and external door, we only measure the center pane. So only the center of the windows, but except the frames of the windows and the doors. So the windows perform a bit worse than design U value, and the door perform better than the design value. Air permeability rate is much higher than the design values, and Grant already talked about the reason for those. So the blower door test shown in here can measure the air permeability rate, and this little device measures the coheating test, which generates the heat transfer coefficient. So Grant has talked about measuring the heat transfer coefficient using coheating test in an actual environment. We can also do that in Design Builder by mimicking the coheating test in Design Builder. So we use the geometry we just built, and we put each thermal zone to inactive. Occupancy density is set to 0, and occupancy scheduling is turned off. Lighting is permanently off. No natural ventilation as doors are closed. Heating is assumed to be on 24/7 using electron convectors with a COP of 1.0. And then weather data is modified to reflect the condition monitored in Energy House 2. So the heat transfer coefficient is essentially a measure of the overall thermal performance of a building. It quantifies the rates at which heat is lost from the interior of the house to the exterior environment under steady state conditions. So just like the coheating test, we can calculate the heat transfer coefficient in Design Builder by dividing the power of the electric heaters by the temperature difference. So for example, in day 1, the total power measured in an electric heater is 1183.4 watts, and the temperature difference is 15.7 because the chamber temperature is 5.3 and the inner temperature is maintained at 21 degrees. So the heat transfer coefficient is 75.4 watts per Kelvin. We have done the coheating test for 8 days. So in Design Builder is also simulate for 8 days. We get a very similar heat transfer coefficient for the 8 days, and the average design HTC is 75.4. So SEP is for the energy rating of the dwellings. It's a methodology currently used by the governments to estimate the energy performance of homes. The current version is SEP 10.2. It is a steady state calculation software, which unlike Design Builder is dynamic. Therefore, SEP can calculate the heat transfer coefficient directly by just summing the heat transfer coefficient of fabric, ventilation, and thermal bridging. So you can see here, the fabric heat transfer coefficient is 55.1, thermal bridging 12.3, and infiltration 8.9. So here, this graph shows the results of the step-by-step calibration. The y-axis is the heat transfer coefficient. The blue bar is the heat transfer coefficient measured using coheating test, and it is 82.2. Here shows the stage 1 design using design U values and design air permeability model using Design Builder, and it is 75.4, which is the value I just showed in the previous slides, calculated through averaging 8 days of the measurement, 8 days of in Design Builder. Here is the same stage 1 design U values and air permeability models using SEP, and it's 76.3. So from the previous slides, also adding the HTC F, V, and B together. And then stage 2 is as-built PDT U and U values and design air permeability, and it shows a bit higher HTC than using the design because the as-built U value for the loft and the ground floor is a bit higher than the design U values. And then stage 3, we use design U values, but then as-built air permeability. And you can see the HTC is much higher because the measured air permeability is 4, whereas the design is 2.5. If you use both as-built PDT values and air permeability, it becomes 81.6 for the heat transfer coefficient, which is very similar to what measured in a coheating test. In SEP, it's also quite similar. It's 84.3, though it overestimating a bit when compared to coheating tests. So after we having the calibrated model of the building fabric, we can put design builder defaults for heating, occupancy, lighting, and heating schedules and density. We put the heat source as air source heat pump. It's a Panasonic heat pump which uses R32 refrigerants to deliver 5 kWh of heating with a COP of 3.01 at 55 degrees, assuming radiant heating. For domestic hot water, it's assumed same as HVAC in design builder. Renewable energy, we use PV, and it's a battery installation and a solar PV inverter paired with a Garwatt battery system with 6.5 kWh of energy storage. Lighting is LED, normalized power density of 2.5 watts per meter square per 100 lux. Ventilation is DMEV, Triton TP640 units located in the kitchen, downstairs, WC, bathroom, and ensuite, and it's a ducted systems. So now we can generate the electricity of the whole year in design builder, and you can see the heating is around 500, domestic hot water is 700, lighting around 700, computer equipment is around 111, and you can see the benefits of putting the heat pumps with a COP of 3.1 really lower the heating of the houses by quite a lot, and also the good fabric performance of the house. For monthly variations, the heating, of course, is the highest in the winter months, and all the DHW lighting and computer equipment are fairly constant through the year. So we can do a very simple calculation of adding the electricity consumption with a total consumption of 3,097 kWh. We assumes 27.35 pence per kilowatt-hour and daily standing charge of 53 pence per kilowatt-hour at December 2023. It has an operating cost of around £1,000. And assuming the PV panels generate 4,100 kilowatt-hours electricity, it can produce an excess of around 1,100 kilowatt-hour compared to its consumption. So if we assume smart export guarantee tariff with a fixed rate of 4.1 pence per kilowatt-hour, in the design builder model, we can see a surplus of 45.1 paid to the owner in the Bellway house. So it's a kind of a low carbon net zero building. So we have limitations in this study, and we use design builder defaults when putting the calibrated model to model electricity consumption. And we also apply simple HVAC and exclude PV modeling. And design builder predict an HTC of 0.7% lower than the coheating test, and SEP predict an HTC 2.6% higher after updating the U values and air permeability rate using things measured on site. This performance, of course, is significantly better than the designer expects HT variations of 6% up to 140% according to literatures with 25 new UK residential buildings. So the whole of this presentation was presented at the CIPC Technical Symposium 2024, and the conference paper will be published soon. And we will calibrate another future home called the eHome 2. And we are working on a journal paper that will be published soon, focused on calibrating the heat transfer coefficient of the future home and eHome 2. And we are also planning to open source data on the Energy House website. So here are the reference, and thanks for listening to all of our presentations.
Okay. Thank you for all of the presenters. And we have 5-6 questions under the Q&A. Should we just go to the question now? The first one from Yensa. How could the solar radiation, both direct and diffused, be emitted in the energy house?
So it's more infrared radiation from the sun that we can replicate. We have large infrared lamps on arrays that we can aim and direct at the properties in different directions. So it's more for solar heat gain as opposed to lighting. And although it is the right spectrum to do some transmission through glazing, it's never going to replicate pure solar radiation, but we can add that heat gain to the property through the IR lights.
Yeah, I hope that's answer your question, Yensab. And then I will go to the next question from Julian. Actually, Julian have two questions. I will ask these two questions together to the presenter. So the first one, did you try to estimate the thermal performance in unstable condition, winter and summer condition, use your climate chamber? That's the first question from Julian. And also, have you also measure air quality in the house, such as the CO2, these kinds of pollutions, or any particular pollutions? So that's two questions from Julian.
Okay, so to answer question one, all the tests in the fabric report and that are presented today were conducted in steady state environment. We have got the capability to replicate weather profiles, so day and night cycles, and change them on a day-to-day basis. And we have done that extensively at Energy House 1. We haven't done any measurements based around that yet at Energy House 2, but we have got plans to do that, especially as part of the overheating set of testing we're going to be doing, which is going to have a diannual cycle, and then also have solar radiation going up to a peak midday and then tailoring off. So we haven't got any results from that yet, but yes, we can certainly do it, and we'll be looking at it. For question two, in terms of air quality, we're about to start doing work on that in about 2 weeks' time in the future home. So we will be looking at how different gases move around the property, looking at background VOCs and different pollutants peak within the property and then also move around the home. So if you had, say, a scented candle upstairs, how does it transfer about the property? And how can you also clean the air within the property? And is the MVHR and DMEV systems working correctly? So yeah, we're about to look at that.
Okay, thank you. And the next question, Hamani asked Grant directly. So Grant, that's your task again. How do you measure the heat loss? Just measure of 1 second? If so, how do you model it for the whole year? So the second part maybe also link with Chris as well, the second part of the question. Yeah.
Yeah. So the first part, as I said, we look at 24-hour steady state conditions. So we measure on all our sensors. We have about 200 plus sensors per house, measure a 1 minute time interval. So our temporal resolution is quite high. So we measure the power data and average it over 24-hour period. We measure temperature data, and that gives us the heat transfer coefficient. Similarly, when we look at the heat flux plates, that's all on a 1 minute resolution as well. So we can see how it fluctuates, but as I said, it was under steady state conditions. You'll have, when we come to do the varying external temperatures, you'll have discharge and charging of the building fabric. So that's something we'll look at in the measurement, but that's something more that Chris is going to be look at first with his model. So Chris, I don't know if you want to jump in.
Yeah, so okay. So the steady state measurement measures the heat transfer coefficient of the building, which Grant has talked about. The minute intervals gives the 8 days heat transfer coefficient measured in the house. And then we put the heat transfer coefficient compare with the co-heating test, which is quite similar. And then this model updates the U values of the house and the air permeability. Will put the standard design builder conditions and then modeled the whole annual performance by putting the Manchester weather file and the electricity consumption of the heating, hot water, and the lighting are presented in the figures. And about the charging and the discharging of the fabric, we will look about those in the future by maybe modeling the thermal mass of the building and see how the maybe furniture affects things in the building. And also we will have plans to model the heating systems more detailed, because currently we only use design builder defaults, which may not be very accurate.
Yes, thank you, Chris. I think next question also link with the last question from Christine. What is the estimate error of the HTC for the modeling? How the temperature of the ground was taken into account for estimation of the HTC? So maybe Chris, you can give a little bit more in detail about the error of the HTC in modeling.
That's a very good question. So in this paper and presentation, I didn't take the error of HTC in modeling. There's the HTC errors in the co-heating test, which is 82.2 plus or minus 1.8. I only do the calibration steps, step 1, step 2, step 3, step 4 in the HTC. And the ground temperature, we will update because we have a soil pit in the energy house too, and we have some measured data in the ground. So in the model, which is published later or in the paper, we will update the ground floor temperature to better reflect the heat transfer coefficient of the model.
Thank you, Chris. And the next question is about the air tightness. How to model air tightness in Design Builder more accurate by insert of the air permeability at 50 Pascal value or infiltration rate for each zone of the zone level. So how you detail model the air tightness in Design Builder. Chris.
Again, it's a very good question. And of course, we will look at this in the future. So currently, we only put the 50 Pascal, the air permeability rate, meter square per meter square at 50 Pascal values in Design Builder. And we could use like some of Design Builders like airflow measurements, airflow modeling. So network airflow modeling. Sorry, I don't remember the exact terms, but there's Design Builder specific modeling tool which can model the air infiltration and air permeability in more detail, which of course we will look at it in detail later on using the data measured from the energy house.
Yeah, I have a question, Chris. I think Ron mentioned you use both blue air traditional methods and the more innovative pulse methods. And the pulse methods actually measure air tightness as a normal pressure level. So do you think this kind of comparison you can also simulate in the modeling? One is based on 50 Pascal, one is based on the normal pressure.
Yeah, it could be.
And you see the physical measure data ground present. Both methods have a different, slightly different measurement results. So it's quite interesting to see how you can compare and find why and which one in which kind of scenarios is more accurate.
Yeah,
that's possible.
So that's part of the plan to investigate the air tightness testing results. So currently in the model, we use the results from the blower door test, but not the other tests.
Okay, thank you. And the next question from Sarbeha. Are you also considering building exact house outside, experience the real weather condition and measure the parameters to understand how close the made up condition work as compared to the real condition?
Yeah, so I can come up there. We have a facility under Henshaw Labs called the Salford Smart Home. That was built by Barrett's. I think it was around in 2020. So that is built in the real environment. It's relatively pretty much a good copy and very similar to the property they've built inside the chamber at Henshaw too. So yeah, we can do the real world experiments. It has multiple heating systems, and although the future home standard wasn't available back in 2020, it's achieving quite similar heat loss and design spec to the future home standard. So yeah, we have got a facility in the real world.
Thank you, Grant. And the next question from Christine again. Is the measure data obtained on Energy House available? I mean, the publish for the open available platform.
So the reports are available if you search the Future Home Baseline Fabric Performance report. You'll see a link. You'll be one of the first ones in Google to the report there. A lot of the data is displayed in there, but the raw data, because as I said, we collect from over 200 sensors every minute. There isn't a way to package that up in a nice and tidy way. But the reports are fully available, and feel free to get in touch if you'd want to discuss that further.
Yeah, thank you, Grant. Yeah, Christine, I certainly know the website from the Salford University Energy House. They publish a lot of detailed report, which you can easily just Google search. So if you're interested, you can either Google search by yourself or contact the team. Yeah, that's all of the questions so far under the Q&A. We still have 4 more minutes left. Any more question from audience? Okay, if no more question, I will promote some future event with, let me see. Okay, so screen.
There are a couple of more questions.
Oh, one more question. Let me see. Oh, yeah. The last question. I'm working in CFC and I want to combine it by PCM, and I want to make a new materials around the PCM, but I need help. Can I send my proposal? I think you definitely can send the proposal, but any presenter can answer a little bit more in detail based on your experience.
I will advise to get in touch with us.
Okay.
Can I just jump in about the previous question? Is it possible to measure cooling loss like heat loss you did?
Okay, yeah. Sorry, I missed that question. Thank you.
Yeah, no problem. So it's something we're about to start looking at. There has been a new IEA annex started, so international piece of research, and it's going to be headed up by Salford University, UCL, and Loughborough. But it is an international piece of research, and one of the key aspects that we're hoping to answer in this new annex is how to measure cooling loss, and can we get HCC in cooling dominated climates. So it's something we are definitely looking at, and please get in touch if you'd be interested in joining that annex.
Thank you, Grant, to pick up this question. And finally, I will promote 2 more coming events from our ABSA education group. The first one, actually 2 hours later, we have a quite interesting topic about building interface design and consideration for simulation. That's from our colleague based in USA, Julie Day, will present his research based on this webinar 2 hours later. You can scan the QR code to join the webinar. And then next week, next Thursday, 4 o'clock, we have another webinar, design of the sequences of the operation for occupant center control by break. So again, same, you can scan the QR code on the screen to join that webinar. So welcome everybody join our coming webinars. Yeah, also you can register our platform, join as a member of the IBESA group. So that's our website, and also we have our LinkedIn page as well. So you can scan the QR code, join us. We will continue promote our event activity under the LinkedIn page. So again, thank you for everybody joining our webinar today, and especially thank you for all of the colleagues from Salford introduce this interesting topic and their case study. We just keep in touch. Thank you.